in the last lecture we have found out the generic expression for mode shape. Now, we are going to solve that for different boundary conditions. So, first the simplistic case of a simply supported Euler-Bernoulli beam is considered. To both the end at x equal to 0, at x equal to 0 and x equal to L is simply supported, that is it is free to rotate, but the transverse displacement is not allowed. So, phi x for a generic case is So, this is the equation that we solved in the last lecture. So, our job is to find out the unknown constants C1, C2, C3 and C4 and also beta by using the boundary conditions. So, let us see what are the boundary conditions. The boundary conditions are at x equal to 0, y 0 t has to be equal to 0, because no displacement is allowed, and the moment is going to be 0, because no externally applied moment is acting there. So, these are the two boundary conditions at x equal to 0. Similarly, at x equal to L, we have y L comma t is equal to 0 and the moment so this is the two set of boundary conditions that we have. Please note that there are 4 boundary conditions and we have to solve for 4 number of unknowns, and so this is a doable problem. So, let me write down the boundary conditions in a more detailed way. So, if what does y 0 t denotes? It is under normal mode of vibration phi 0 and T t equals to 0. Okay. T t cannot be 0 for all possibilities. So, therefore, phi 0 is equal to 0. And similarly, E I del 2 y by del x square at x equal to 0 is going to be E I phi double dot 0 which should give us so these are the two sets of equation that we have, boundary conditions that we have. If we try to impose this, then what is phi 0? Phi 0 is going to be, so C1 sin beta 0 is 0. C2 cos beta 0 is C2, C3 sin h beta x is 0 and C4 is 0. So, I have this is my equation 1. Now, what is phi double dash 0? That is minus beta square C 1 sin beta 0 So, that is again equal to 0. So, what do we get out of it? This goes to 0, this goes to 0. So, I get minus C 2 plus C 4 is equal to 0. So, this is my second equation. Now, from equation 1 and 2, we can get that C 2 equals to 0 and C 4 equals to 0. So, we are left with, so my phi x turns out to be C 2 cos beta x plus C 4 cos h beta x. So, this is the simplified equation that I get. Now, sorry, this is going to be C 3. So, this is, oh, I am sorry about this equation. C 2 and C 4 are equals to 0. So, my this one is C 1 sin beta x plus C 3 So, I have simplified the generic expression of phi x for this simply supported case. Now, what I have to do is to impose the other two boundary condition and find out C 1 and C 3. So, if we do that, I have, let me again write it down, I have this as C 1 Now, what is phi L? Phi L is C 1 sin beta L plus C 3 sin h beta L, and that is equal to 0. What is phi double dash L? Phi double dash L is minus beta square C 1 sin beta L plus beta square this can further be written as minus C 1 sin beta L plus C 3 sin h beta L equals to 0. So, if I call this as equation 3, I call this as equation 4, then from equation 3 and 4 we get C 1 sin beta L is equal to 0 and C 3 sin h beta L is equal to 0. Now, let us look into this two solution. Sin h beta L can never be equal to 0. So, this gives me C 3 equals to 0. So, my phi x gets even more simplified and it becomes C 1 sin beta x. Now, my job is to find out C1. Now, let us see what are the possible solution for C1. So, what I have C1 sin beta L equals to 0. Now, C1 cannot be equal to 0. If C1 equals to 0, then phi x becomes equal to 0, which is a trivial solution. So, C1 cannot be equal to 0. Therefore, my sin beta L has to be equal to 0. So, how will sin beta L become equal to 0? When beta L is r into pi, where r could be anything, r could be 0, 1, 2, 3 and so on, all possible integer values. Now, let us see, r should not be equal to 0, because if r is equal to 0, then this again becomes a trivial solution. If r equals to 0, beta is equal to 0 and then this becomes a trivial solution. So, r cannot be equal to 0. So, this part is gone. So, r could be 1, 2, 3 till n. I should mention here that r equals to 0 also cannot be a physical solution, because r equals to 0 denotes beta equals to 0, which in turns denote omega equals to 0. Omega equals to 0 is a possible solution only when there is a rigid body mode. So, we have seen earlier, when a system has a rigid body mode, only then beta is only then the natural frequency is 0, but since the simply supported beam has no unconstrained degree of freedom, it cannot have a rigid body mode. So, omega equals to 0 is not physically acceptable solution of the system. Here we also see that omega equals to 0, which means beta equals to 0 is also mathematically not a solution of the system. So, therefore, my phi x solution, therefore, beta L is going to be r pi, where r is all possible integer values. So, phi x therefore turns out to be C. I can drop the subscript because anyhow there is only one constant. So, I put a subscript r to denote rth mode, then I have sin pi r x by L. So, this is the mode shape of the system. So, let me write it in a clear way. So, I have phi x r, that is the rth normal mode. Mode shape for rth normal mode is C r sin pi r x by L, where r is equal to 1, 2, 3 and all the possible integer value. So, this is the mode shape. So, what is the rth natural frequency? Let us try to find out. So, we have seen that beta is pi r by L. Therefore, beta 4 is pi 4 r 4 by L 4, and which is equal to omega square m by E r. So, this gives me omega as pi square r square L square root over E I by m. Therefore, the rth natural frequency omega r is pi square r square L square. So, Therefore, these are the natural frequencies and mode shape of a simply supported beam. With uniform cross section. Now, the next thing that I should mention here, that similar to the rod, here also the mode shapes are orthogonal to each other. So, orthogonality can be expressed as the integral So, this is the orthogonality of the mode shape. We can check for any two independent mode, this integral has to be equal to 0. So, we can do that for the case of a simply supported beam as well. The next job is to find out the mass normalized mode shape. So, how would you find out the mass normalized mode shape? I have to take phi r x m x phi r x dx and forcefully make this equal to 1. So, for our case, if we mass normalized, we will have 0 to L C r square sin square pi r x by L into m into dx. Sorry for this mistake, this should be equal to 1. So, that should be force to 1. If we solve this, we will see that C r turns out to be 2 by m L. Therefore, the mass normalized mode shape phi r x mass normalized is going to be 2 by m L into sin pi r x by L. So, this is the mass normalized mode shape. So, now we will move on to our next problem, where we will try to find out the mode shape and natural frequency of a fixed free beam. So, let us move on to a fixed free beam. So, here we have at x equal to 0, we have the end to be fixed, and at x equal to L it is free. So, let me write down the generic expression for phi x, which was C1 This is the expression that I have. Now, I have to impose the boundary conditions. So, let us look into what are the boundary conditions. So, the boundary conditions are at x equal to 0, what do I have? I have y 0 t is equal to 0. The other that I have is the slope is equal to 0, equals to 0, or this can also be written as y dash 0 L t is equal to 0, because at the fixed end no rotation is also allowed. The displacement is not allowed for sure, and the rotation is also not allowed. So, I have y dash 0 t equals to 0. So, let us look into the next set of boundary condition, that is at x equal to L. At x equal to L, I have free end. So, the applied moment is equal to 0. So, how can I write that? I can write that as E I del 2 y by del x square is equal to 0. And the applied shear force is also equal to 0. So, V x comma t or q x comma t, as we have said, is equal to 0. So, I can write E I del 3 y by del x cube is equal to 0, because the expression for shear force is E I del 3 w by del 3 y by del x cube, and the expression for moment is E I del 2 y by del x square equals to 0. Now, we have to impose this boundary condition on this phi x, and we have to find out the unknown constant. So, let us try to do that. So, y 0 t is phi 0 into t t, and that is equal to 0, and this implies phi 0 is equal to 0. Now, y dash 0 t is phi dash 0, that implies phi dash 0 equals to 0. Now, if we impose this condition, phi 0 is equal to C 2 plus C 4, and that is equal to 0. Phi dash 0 is equal to C. What is phi dash 0? Phi dash 0 is minus beta, plus beta C 1 cos beta 0 plus minus beta C 2 sin beta 0 plus beta C 3 cos h beta 0 plus beta C 4, and that is equals to 0. So, that gives me C 1 plus C 3 is equal to 0. So, let me call this as equation 1 and this as equation 2. So, if we impose equation 1 and equation 2 into my generic solution for phi x, then what do I get? I get C 4 is equal to, so I get C 1 sin beta x plus C 2 cos beta x minus C 1 sin h beta x minus C 2 cos h beta x. Now, I have simplified the equation. The two unknowns left are C 1 and C 2. We will find out C 1 and C 2 from the other two boundary conditions. So, let us try to do that. So, the other two boundary condition is y double dash L comma t is equal to 0. That implies phi double dash L is equal to 0. The other equation that I get is, of course, there is an E I here. Now, if I try to evaluate phi double dash x, what do I get? I get C1. So, similarly, phi triple dash x is going to be C1. So, if I write down therefore phi double dash L, what I get is equals to 0, which gives me C1 sin beta L. Now, this two equation can be written in matrix form as okay. So, these are the matrix equation matrix form of the equation that we get. Now, we know for since the right hand side is equal to 0, for non trivial solution of C1 and C2, the determinant of this matrix has to be equal to 0. So, therefore, the determinant of this matrix, let me write it down. Is equal to 0. So, if I solve this matrix equation, I am going to get the solution as cos beta L into cos H beta L is equal to minus 1. This is what we get. Now, what we have to do? So, we do not get a straightforward direct solution for beta, rather we get the value of beta in terms of a trigonometric equation. So, if I solve this equation, I will see the root for B L is equal to 1 So, this can be numerically solved. I have solved this and got the solutions as 1.8715 and then 4.6941, 7.8548 and then 10.996 and so on. We can find out infinite number of solutions for beta L. So, if this is the solution for beta L, from this solution we can always find out the solutions for omega. Okay. So, we can find out infinite solutions of omega. So, you can find out omega 1, omega 2, omega 3 and so on till omega r and so on. Okay. So, these are going to give me the natural frequencies of the system, and once we find out beta L, once we find out beta L, I can find out the values of C1 and C2, the relative value of C1 and C2. So, once the relative value of C1 and C2 are known, we can find out the solution for phi x. This should be known. So, phi r x and omega r is going to be known. So, this is going to be the solution of the mode shape and natural frequency of a fixed free beam. So, with this I will end this lecture. In the next lecture, we will solve another problem of a beam where a rigid body mode is present, and we will see that there is a solution omega equals to 0 solution, and we will also prove the orthogonality of mode shape for an Euler-Bernoulli beam. Thank you.